Welcome, this is Mrs. Rutchling. This chapter is an abbreviated form of Chapter 19. We're looking at entropy and free energy and how that affects the spontaneity of a reaction. Most college textbooks say spontaneous. You have to substitute the word in thermodynamically favored. That is the preferred terminology for the College Board. Looking at thermodynamics, they tell us the direction. Is the reaction going to go towards the products or the reactants? They only look at the initial and final states. Thermodynamics is not considering the pathway. That's kinetics. So we have to use both of these to understand a reaction completely. The first law of thermodynamics says that energy can't be created or destroyed. So the total energy of the universe is constant. That means that if total energy is conserved, that reaction can proceed. However, it doesn't really explain all we see. For example, this broken cup, the first law would say, yes, it is possible for this cup to reassemble itself. Since this doesn't happen, it tells us that the conservation of energy isn't the whole story. We're going to talk a little bit about order to disorder. Natural processes tend to move toward a state of greater disorder. Some examples: if you like sugar in your coffee, you stir it in, the sugar is spread out and you can't stir it to get the sugar back out. A tornado hits a building. It doesn't ever assemble it, it always destroys it. You don't see a lake spontaneously freeze on a warm day. So the first law says those could all happen, but the second law says they won't. Thermodynamically favored processes are those that can proceed without any outside intervention. We have a vessel A and a vessel B, and they're attached, and in between is a stopcock, similar to that on a burette. In the perpendicular position, it is closed. This is a vacuum, and there is a gas creating 1 atm in B. If they are open, the gases will spread evenly throughout. Going from the top to the bottom is thermodynamically favored. Going from the bottom to the top is not. When you're looking at thermodynamically favored processes, you need to look at temperature. So if I have a flask of ice at a temperature above 0, it is thermodynamically favored for that to melt. Below 0 is thermodynamically favored for it to freeze, so temperature plays a role. A reaction that's thermodynamically favored will proceed without outside intervention. All of these don't have anything to do with the thermodynamically favored part. A reversible process, the system changes, but it can be put back in its original state by exactly reversing the process. And many of our chemical reactions that we looked at are similar to this. A reminder that if something is exothermic, the change in enthalpy will be less than 0 or negative. And if it's endothermic, it'll be greater than 0. An irreversible process can't be undone by exactly reversing the change. Entropy is abbreviated with a capital S, and lots of times it's described as a measurement of the randomness. It's really more about dispersing the matter of energy, and it can do that depending on the number of arrangements available to that system. How can the particles be arranged? These are called microstates. Like total energy and enthalpy, it's a state function. That means I can look at the initial and final, find the difference, and calculate the change in entropy. Looking at a particular molecule, there's different types of motion. Translational, the molecule moves from one place to another. Vibrational, where it is vibrating. And rotation, where it actually rotates about its axis. A microstate is a snapshot of the molecules. How many different ways can it be arranged? If we start with 4 particles in this uniquely shaped vessel, 3 particles on the left side and 1 on the right, gives us 4 different arrangements based on which particle is on the right. 2 and 2 is going to give us 6 more based on the combinations. Now we have the opposite, 3 particles on the right and 1 on the left. Again, there are another 4. And all 4 on the right. These are all possible microstates or possible positions. If I increase the possible microstates, I increase the entropy. S values are assigned to substances, and those are based on the third law of thermodynamics. Entropy is 0 for a perfect crystal at 0 Kelvin. This is theoretical since we have not had anything at 0 Kelvin, but it is a standard value and it helps us estimate our change in entropy. Since entropy is a state function, we can subtract the final and initial in the same way that we did for change in enthalpy. For entropy, you have to look up all the values. There is a value for each substance, even the elements. Remember, for change in enthalpy, the elements have values of 0. Entropy is extensive, meaning that it depends on the number of moles. So we do need to include that in our equation. Pause the video and give this one a try. I have 1 C2H4, so I look across for my value, 219, plug that value in, then I subtract the values for the reactants. I've put the number of moles and the entropy values. Pause the video and give this one a try. This problem, I do not have a 1-to-1 ratio, so it's important to put the moles in. I substitute in my values and I get a change in entropy for this reaction of negative 149 joules per Kelvin. Going back to the second law of thermodynamics, when we're talking about the increase of entropy of the universe, we're looking at the change in entropy for the system and the surroundings. Looking at the change in entropy, if it is greater than 0, it is thermodynamically favored, and that means that it is irreversible. At equilibrium, change in entropy is going to be 0. If it is not thermodynamically favored, the change in entropy is going to be less than 0. It is going to be reversible. That means that the entropy of the universe is always increasing because there are always some sort of thermodynamically favored process going on. Gibbs free energy combines these two ideas, enthalpy and entropy, and gives it one value. The change in free energy can be used to predict the direction of the chemical reaction as long as we have a constant temperature and constant pressure, and we will have that for this year. The degree sign represents the standard states, and that's the most stable state of that compound or element at 25 degrees Celsius and 1 atm. Change in free energy at standard state is the one that we shall be using. If the change in Gibbs free energy is negative, so if we're going down, it's negative, the forward reaction is thermodynamically favored, going from the reactants to the products. If the change in free energy is 0, Q equals K, and we are at equilibrium. If the change in entropy is positive, if Q is greater than K, then the reaction is thermodynamically favored in the reverse. Comparing our values, if K is less than 1, the change in free energy is positive. This means it is not thermodynamically favored and that the reactants are favored. If K is equal to 1, the change in entropy will be 0 and we are at equilibrium. If K is greater than 1, the change in free energy will be negative, and this is a thermodynamically favored process, meaning it will proceed towards the products. This is an important slide to know. Change in enthalpy values and entropy values for sodium chloride and its substituent ions and silver chloride and its ions. Calculate change in enthalpy, the change in entropy, and finally the change in free energy at 298 Kelvin. Starting with change in enthalpy. We're using products minus reactants. This equation is on your equation sheet. Plugging in the values from the table, and noticing that we have a 1-to-1 relationship, we find that the change in enthalpy is a positive 3.6 kilojoules. Doing the same sort of calculation for entropy, we find that our entropy is plus 43.2 joules per Kelvin. And I've gone ahead and changed it to kilojoules so that we have like units. Lastly, we want to calculate the change in free energy. We use our calculation. We have come up with the change in enthalpy, we have calculated the change in entropy, and we were given our temperature. Substituting those values in, the change in free energy is negative 9.3 kilojoules. This reaction is thermodynamically favored at 298 Kelvin. That should make sense to you because at room temperature, salt dissolves. The same chart is given, and you should do the same calculations for silver chloride. Pause the video, check your calculations. The change in free energy is a positive value. This means it is not thermodynamically favored at room temperature. Again, that should correlate with what you know because silver chloride is not soluble. In fact, it's often a product of reactions that is a solid. Copy your values into these charts for change in enthalpy, change in entropy, and change in free energy. For sodium chloride, the products are favored at room temperature because we have a change in free energy of negative 9.3. At room temperature, the reactants for silver chloride are favored because we have a positive change in free energy. How does that compare to our KSP? Based on our change in free energy, we know the KSP must be greater than 1, and it is in fact 43. Based on our positive change in free energy, we know the KSP must be less than 1, and it is quite a bit smaller, 1.9 times 10 to the negative 10th.